Yeah, that's a really tricky one.
There's some pretty beefy ones going on.
Dude, I want a Jeep so bad.
Isn't it 87 per pound? It's like 2,000.
I don't want
to get it running.
like, I kind of want a stick, but I just really need to go and have a break.
His is automatic, but I'll get it like 4 high, 4 low. It's fun.
All right, so Donovan, do you have an answer for 2A for us? For 2A, yeah, for 2A, please. Looks good, very good. Okay, everyone else okay with that? X cubed minus 3x squared plus 5x minus 15. Anyone need to see it done? We're all good there? Okay, very good. So yeah, that is correct. All right, the setup here, if you wanted to see it, we're integrating again from 3 to x of 3t squared minus 6t plus 5. And then integrating that, we end up with t cubed minus 3t squared plus 5t evaluated from 3 to x. And then when you plug the x in and subtract the 3 plugged in, your upper limit minus your lower limit, you get this right there. Okay, good. And so then we take the derivative here of that. Let's go to Tyler. What'd you get for letter B then?
3x squared minus
6x plus 5. That's right. Okay. So, do we see a pattern here, a relationship, when we are going to these letter B's where we're taking the derivatives of the integrals? What ends up really just happening here? What switches?
The variables.
The variables, right? Okay, so instead, the x kind of replaces the t, right? The derivative of an integral, the x kind of goes in, replaces the t, so we get 2x plus 3, right? The x here goes in, replaces g of t. Instead of g of t, we say g of x. G of t was 3t squared minus 6t plus 5. The derivative of the integral of g of t becomes 3x squared minus 6x plus 5. So again, all that changes is that just the x's plug in there. Okay, so this is what we're going to be using in the future to find the derivative of the integral from a number, to x of a function when a is a constant. Okay, so that's what we're going to be doing here. So, well, what would this then, what is the derivative, this very abstract kind of derivative, because there's lots of letters here, no numbers, but what would we expect this to equal then? If we take, the derivative with respect to x, not t. If we take the derivative with respect to x of this function, what's going to change? It's going to be j of, just j of x. That's all it changes. Just j of x there. All right? So now let's look at another one here. Let's change things up just a little bit. All right, for these next 3 and 4 here. Okay, so 3, our function k of t is cosine of t. So here we want to find the integral. Now what's weird about this integral?
It's not just x.
It's not just x, it's 2x squared. So let's see how this will end up when we go to take the derivative of that integral. Let's see how that's going to change things. We expect it probably is going to change something, right? Otherwise we wouldn't devote a whole section here to just looking at that. But we're not really sure how, maybe. Okay, so I'm going to replace k of t with cosine t. To do this integral, we're still going to integrate as we normally would. Okay, what is the integral of cosine? Let's go to Nate. Integral of cosine?
Negative sign.
Close. Just sine. Just sine. So sine of t, and they're going to evaluate that from 6 to 2x squared. All right, so that integral wasn't that big of a deal. The same thing with the evaluation, not that big of a deal either. We'll just have sine of 2x squared minus sine of 6. All right. Can we simplify that any further?
Find sine of 6.
We could plug in sine of 6, yeah, but again, it's like it doesn't really, it doesn't make it look any nicer. It's still gonna be messy. So in other words, no. Okay. All right, great. So now we're going to take that integral, and we're going to see what happens when we go to take the derivative of the integral from 6 to x of k of t. So if I take the derivative of this thing, all right, derivative of sine of 2x squared. Let's go to Brandon. Derivative of sine is cosine, and it's going to be cosine what? Derivative of sine of 2x squared is going to be cosine 2x squared as well. That's okay, I know. That's where we're cleaning the cobwebs out. Some other people are like, phew, yeah, it's 4x. Very good. We multiply by the derivative of what's inside. That's called the chain rule we did there. It's the chain rule, right? Okay? And then what's the derivative of sine of 6, Brandon? Minus cosine. What is it? It's 0, because sine of 6 is a number. And I started leading you that way on purpose because, you know, I know that's a common way to think, because we see sine, like, derivative of sine is cosine, but it's sine of 6, so it's really just considered a number. So it'd be 0. Right there. Okay, now, let's look at what this resulted in. Okay, before, up here in 1b and 2b, when we took the derivative, okay, of an integral from 1 to x, so here we took the derivative of the integral from 3 to x of our functions, the only thing that changed was what? The t's were replaced with x, okay? If we look down here, when we took the derivative of an integral from 6 to 2x squared of our function, does the t get replaced with 2x squared? It does, right? Instead of cosine of t, it's now cosine 2x squared. But one other thing, we have to multiply by what? The derivative of that limit that we plugged in. Okay, so you see that here? The derivative of the integral, like Tyler was saying earlier, does still kind of cancel out. It does kind of cancel it out. The 2x squared still does go in, replacing the t. However, because of the chain rule, we then have to multiply by the derivative of what's inside times 4x. That's it. That's the only change there. Okay? So, let's see if we can try this one. So you guys go ahead and try number 4. See if it works for number 4 as well. Good. So try 4a, do this integral, and then take the derivative of that. Excuse me, and I will do it as well. Actually, no, I won't do it. I'll come around and kind of help as necessary. All right, so again, we're going to do the integral from 3 to cosine of x. Of e to the t dt. Okay. So you have to remember how to integrate with the t. Good. Yep. When you integrate into t, it's just the that's no need to just so first you're going to evaluate that from 0 to, then we start with 3 to go ahead. Good. Cosine times. Wasn't this so far? Good. Yeah, it'd be upper minus lower. No, it's okay. Noise.
You have to multiply e by the antiderivative of cosine of x in integral, correct?
When you, okay, in letter A you're saying?
Yeah.
You just need to do the substitution, that's it. There's no worry about
Okay.
integrating cosine itself, the limit of integration. Alright, Christian! Integral of e to the t is?
E to the cosine of x minus e cubed.
Okay, so yeah, you got one step ahead of me there, sorry. Just integrating e to the t yields e to the t, and then we'll plug in those limits, and you're right. You knew the answer. Okay, minus e cubed is our answer there. So again, we're going to take that integral, the definite integral is equal to this, we're going to now take the derivative of it, so we want to take the derivative of, whoops, I guess I can use the brackets there, e to the cosine x minus e to the 3, and we'll go to Austin for that one.
Okay.
Derivative of e to the cosine x is?
Negative sine x e cosine x.
Okay, so yeah, the derivative of e to the cosine x is e to the cosine x, right, times the derivative of what's inside, which is negative sine of x. Okay, good. And the derivative of e cubed?
Is
0,
0.
right. Folks, it is not 3e squared, right? E is a number. Yes, it looks like a variable. It looks like a variable, right? You might think, oh, it's x. It's e cubed is a number, so the derivative of a number is 0. So it's just this, and so like Austin said, yeah, so we can rewrite that as negative sine x e to the cosine of x. All right, so let's see if our rule kind of applies. Again, remember, in the earlier problems here, when we were taking the derivative of an integral from 1 to x, the only thing that changed from the 2t, they kind of canceled each other out, and the t got replaced by the x there. Right? 2x plus 3 is our final answer. Here as well, the derivative of an integral from 3 to x of g of t, the t just replaced with the x, right? It was 3t squared minus 6t plus 5, now it's 3x squared minus 6x plus 5. Okay. Here, we're taking the derivative of an integral, and so we think to ourselves, do they just cancel out again? And they basically do, right? Cosine of t becomes cosine of 2x squared, though, so we replace that t with the 2x squared, and then times the derivative of what's inside. And then same thing happens here. All right, we're doing e to the t. The cosine of x replaces that t, so it's e to the cosine of x times the derivative of what was inside times the derivative of the thing we plugged in, negative sine of x. So there it is. Okay. So in general, then, this will be equal to, if we take the derivative of an integral from a to a function, the derivative integral will cancel out, and it will be f of what? What's going to replace the t?
F of g of x.
G of x. Yeah, g of x replaces the t times
G prime.
g prime, the derivative of what was inside there. That's true in general. Okay.
I like it.
It's a little bit funky, but once you get it, it's a little weird, but once you get it, it's real easy. It makes things so much easier. That is the second fundamental theorem of calculus. Okay? So the first fundamental theorem, remember, that's what we use when we integrate a definite integral, when we do a definite integral and we evaluate it. Second fundamental theorem is when we take the derivative of a definite integral. Okay? That's all. All right, so if you want to just turn your paper over, we're going to look at some more, we're going to do some practice here on the back. I'm actually going to tell you what the second fundamental theorem of calculus states now. Okay, so question. Yes.
You were saying like the 270 or triangles.
Right.
Is there different forms of calculus?
Are there like branches? I mean, there are, again, you can, that I don't know. I think calculus is pretty well, like, established, I want to say. So, I mean, there are other branches, yes, for sure, you know, but I don't know, yeah, I don't know if it, yeah. Just geometry branches, calculus branches. You can, so don't think maybe of geometry as being like alternate geometries. It's just there are different ways to go with geometry. There are different ways to go with calculus, too. That's all. So like I said, calculus 3, right, that's three-dimensional calculus. So instead of talking about just XY plane, you're not talking about X, Y, and Z plane. And you start, you know, getting some interesting things there. You do like things called partial derivatives, and all sorts of crazy things happen because they add that extra dimension. All right. Here is the second fundamental theorem of calculus. All right. This is a popular kind of question to show up on the AP test. All right? And of course, they're not going to say, use the second fundamental theorem of calculus to answer this question. They're going to give you an integral that has a function as one of the limits of the integral. So I'll show you an example here. First, let's define it here. So if f is continuous on an open interval, then for every x, and then for every x in the interval, there it is, that's what I want to see, okay, in the interval, the derivative with respect to x of the integral from a to u of f of t dt is equal to f of u times u prime.
Why is the bracket closed on the far right?
That is a good question. I shouldn't be over there. You're right. I apologize. That should not be there. I was looking at that. I was like, whoops, that was wrong. Yeah, sorry. So the derivative with respect to x of the integral from a to u of f of t dt, so the derivative of an integral results in you basically just plugging in u, okay, replacing the t with the u there. A is a constant. All right, so let's try an example here real quick. So again, on the AP test, you might just see a problem like this. Evaluate the derivative with respect to x of 3 to 3x minus 2, the integral from 3 to 3x minus 2 of t squared dt. Okay, you might just see a problem like this. Naked problem. No context or anything like that, just do it, right? All right, so when we take the derivative of an integral, they kind of cancel each other out, right? Just like we saw in our earlier, kind of investigation there, they kind of cancel each other out. And our limits here kind of, when we plug in that top limit, we replace t with that. So instead of t squared, it's going to be what squared? 3x minus 2, that upper limit quantity squared, times the derivative of what's inside. So the times the derivative of that 3x minus 2, which is 3. All right? There's the f is the something squared, the u is that 3x minus 2, and then times the derivative of that u, 3. All right? So that's the answer. That's it. That's all the work there is to it. Yes? Shortcuts are what we were just doing, yes, basically. The point of those was to kind of hopefully show you that pattern of what's happening, and then just now we're just going to use that pattern, the shortcut kind of deal, instead of actually like doing it. If you wanted to, Anna, you absolutely could integrate it first, like we did, then get that answer, then take the derivative. That will work. There will be problems, however, they'll be written in such a way that you'll have to use second fundamental theorem calculus. You won't be able to integrate it. Okay.
So with that, you don't have to worry about plugging in that lower limit?
The lower limit, let's remember it this way, right? If I would actually do this by hand, the first thing I would do is integrate t squared. I'd plug in the 3x minus 2, I'd plug in the 3. That lower limit then would just be a number. There's no variables in there. So then when I go to take the derivative of it, what's the derivative of a number? It goes to 0. That's why we ignore that 3, because it's going to be 0. The upper limit we keep, though, because it puts a new variable in there. And so that's why we do that.
Say the lower limit was like x.
Great question! So we're going to find the derivative. And forgive me for cutting you off, Connor, but I think I know what you're going to ask.
No, I didn't do it.
Okay. So we'll start with this. Now, let's just, before we kind of move on and start actually doing what the question's asking, let's kind of appreciate what is going on here, what this thing is saying. You might not appreciate it, but let's at least try and wrap our minds around it, okay? Because if you might look at this and say I don't really know what this means, but let's really talk about this here. So this is a function, and the function is defined to be an integral. So for example, if you guys remember way back in the day when you first learned about functions, you would always make those little t-charts, or wherever you go, xy charts, whatever. You'd pick some x values, and you'd plug those x values into the function, and you get the matching y values. You guys remember doing that?
Yeah.
Right, back in the day. It's like how you first learned how to do functions, probably first learned how to do lines and stuff like that. And your teacher was like, hey, look, when you plot all the points, it makes a straight line. You're like, oh my gosh, your little middle school brains or whatever, maybe not, probably not, but anyway.
It's more like
This function, if we were to make a t-chart for it, we could still pick some x values, but then when we go to plug those x values in, where do the x values plug in for?
T. Wait, no.
Our function here. So again, if I wanted to graph this function, I start plugging in x values. Let's say I want to find f of 1. Where is that 1 going to go? into the lower limit and the upper limit. So that means every time you evaluate this function, you have to then evaluate the integral from x to x squared, okay? Or from, f of 1 from 1 to 1. For f of 2, it would be 2 to 4. F of 3, it would be 3 to 9, so on and so forth,
so
right?
is it like-
You understand the function is an integral. Like it's the actual, like it's a function. This number changes, these are what's changing. Not this. This t is not changing. It's this that's changing because of what number you plug in for x here. That's changing.
I don't see it.
So-
We're working it.
If we graph this, would it be like a parabola with a line going through it, like a semicircle kind of thing?
We'll talk about graphing in just a second here. We'll talk about that in just a second. Let's worry about finding the actual answer to the question. Then we'll talk about what the graph of this would look like. All right. So capital F prime of x is what we want to find, right? We have capital F. We want to find capital F prime then. Find the derivative. And we're going to use the second fundamental theorem of calculus because this equates to us taking the derivative with respect to x of the integral from x to x squared of cosine of t dt, right? If I want to take the derivative of the left-hand side, I have to also take the derivative of the right-hand side, right? It's an equation, so derivative of the left and the right-hand side here. So I'm taking the derivative of this. You don't have to write this step out, by the way, when you're doing your work. I'm just trying to be very explicit here to kind of, give you an idea of what's going on. You will probably jump right into the next step, which is what we're going to do here. So when I take the derivative of an integral, what happens to that integral sign? Goes away. We still keep cosine, but now it's going to be cosine of what? X squared times 2x, the derivative of what's inside there, right? Don't forget that chain rule part. So it's going to be cosine of x squared times 2x. But then our lower limit's no longer a number, it's actually an x. So yes, what do we do with the lower limits? You subtract them minus cosine x
And then the entirety of that.
times the derivative of x, which is just 1. So there it is. This is the derivative. Right there. That's it. So, Connor, to answer your question, when you take the derivative, when you have both a lower x and an upper x, you treat it like you normally would. Take the derivative, plug in x squared for the t, times the derivative of what's inside, minus the lower limit plugged in, times the derivative of what's inside. That's all there is to it.
What if it's just the lower limit to...
We'll get to that. I think I have that next.
Wait,
So,
question.
is that what you're going to ask too?
No, I
Yeah.
was gonna ask,
Or something else.
yeah.
What's your
I was
question?
gonna say, if it doesn't have, find the derivative of, but it just has the derivative,
Oh, like that, then yeah, obviously, yeah. So if it just gives you this, then you do the same thing too.
Question.
Yes.
So, I guess in the definition of the second fundamental theorem, where it says multiply by u prime, that u prime and the one we just did is 2x and then the 1. Or like if we have to multiply the entirety of it.
No, it's the if you looked in the first one that we showed from it's on this side, Doug. This one you're talking about right here.
Yeah.
So if you look, the G, the very first one you're saying?
No, I'm saying...
This one right here.
The first...
Oh, up here, okay, sorry.
So like...
Right here.
We multiplied it by 3.
Keep in mind here, A was a constant.
Yes.
But when you have a different u here, then it'll be f of u times u prime minus f of w times w prime, whatever your lower
Alright,
limit.
so then why don't we multiply the entirety of the derivative by u prime?
Because we will, you're talking about like upper limit, like why don't we multiply both the upper and lower limit by u prime or whatever? Like why don't we multiply both of these by 2x? Is that what you're trying to say?
What I'm saying is like, why don't we,
Because if you imagine, again, if you have to think back to like what the actual steps were that we did. So guys, again, this is Austin's question for those of you that aren't really sure here. He's saying, why don't we multiply both of these things by the derivative of what's inside here, okay, by the 2x. And the idea is this. What do we do first? We would integrate this thing, right? Get negative sign. No, wait, get sine. Sine, okay, it would be sine of x squared minus sine of x. That's the integral. Sine of x squared minus sine of x. But then when we take the derivative of it, we're going to take this derivative of sine of x squared, which is this, minus then the derivative of sine of x, which is that. You see how it's breaking up? Because that the subtraction sign's there, it breaks the two things up into separate kind of derivatives that we're taking, so not multiplying.
So like if we wanted to create just like one that would work for every single problem anywhere, it would just be like the answer would be like f of u times u prime minus f of a
times a prime, if you want to call that. Yep. Yep. Exactly right. Yep. All right. Let's try another one here, and then I'll have you guys try one on your own. All right, so here was the next question. This is Ryan's question. So what happens if we have a number in our top limit, our upper limit, and we have then a function in our lower limit?
It just makes it negative. Would it not?
That's what I thought.
We'll see here. Let me finish writing it out. Okay. And again, same directions. We want to find the derivative of this capital F of x. So we want to find capital F prime of x. All right, so we're going to take the derivative here, and this time I'm not going to write out the derivative with respect to x part. I'm just going to go ahead and do it. All right, since our upper limit's a number, what happens to that upper limit?
It's 0.
It's 0. So you can put a 0 in there if you want to, or you can just put minus then. And then now we're going to plug in our lower limit, right? The lower limit will just replace, in this case, y. So it'll be sine of 3 times 2x minus 1 plus 7. Like that, right? We substitute it in place of the y, replace the 2x minus 1. Times 2. The derivative of what we plugged in. The derivative of what we plugged in. Times 2. Okay?
So it would be unwise to distribute that through that.
No, you could, absolutely. So at this point now, but you multiply by the derivative of what you plugged in, I should say, by the derivative of what you plugged in.
So you shouldn't distribute it until you get to the very end.
Correct, yeah, until you're done with taking the derivative, now let's simplify it. So you're right, so we can pull that 2, make it negative 2 sine, and that becomes what, 6x minus 3 plus 7, so it becomes really negative 2 sine of 6x plus 4. And there is your derivative of the integral.
Oh, boy.
Okay?
Cool.
We could have just gotten that for like the first one, right? The free response question.
Oh yeah, free response question, you can stop right there. So there it is. More than likely though, well, let me think here. More than likely I think you'll see this as multiple choice. More than likely. Alright, let's try another one here. This is for you guys to try. So, try, given...
It cuts off the T and it says rye.
Rye.
No, just let it
Like it's you, for short.
Red.
Your name's too long, so I just call you Rye. Or
Never been called over.
Never been called
Alright, we can stop talking.
Alright, the integral from 2 to 2x of 3t squared minus 5. Okay, so there's our function defined as an integral. So the function is defined as an integral.
I like what you're doing.
First thing I want you to do is find f of 1. I want you to then find f prime of 1. And then I want you to find f prime prime of 1.
Oh man, it's sort of 1BC.
You may not be using the second fundamental theorem of calculus for all 3 of these. Hint, hint. Okay? So really think about what you're being asked to do here. For this first one, f of 1. Think about what you're being asked to do there. Then f prime of 1, there we're now taking a derivative. Think about what that means. Okay? And then second, letter C, we're asked to find the second derivative there. So again, think about what that means. All right, I'll come around and help as necessary here. But you all have the skills to do these. Why are you debating between 2 of these?
That was my mom. It was my mom.
All right, let's try these, guys. Let's try these. This is not for... I'll wait for Mr. Witt to do it, and then I'll get the copy.
So,
Yeah. Yeah. So what would it be?
How do you get that? Oh. One, the zero, careful. The 1 is replacing the x. Here's the x. So b becomes 1, 2. So it's the integral from 2 to 2, which would be. So this would still be a t, because you haven't integrated yet. So that would still be t, but then the idea is integrating from 2 to 2, you know that integral's got to be, you need to actually integrate.
So for this, you do this with minus.
So again, f of 1, that's your function,
Yeah.
f. So.
How'd you do it so
x of
fast?
1 is replacing x. So it'd be 2 times 1. So that from is 2, so it's integral from 2 to 2 of this thing.
Oh, I do.
You have to use the
Never mind. I do.
because,
I do.
no, well, you could, but you don't have to.
So can I just plug in?
Come on there, yeah. If you wanted to now, at this point, yes,
Oh,
you're,
so-
so I'm seeing what you're saying.
No,
I
that's
see
not a
what
big
you're
goose.
saying. Yeah, exactly.
Okay.
Yeah. Yeah, you can integrate though, not wrong,
It's just a lot.
but it's more work, yeah, you don't.
So if you plug in 1.
Just the way.
So, okay, so
And
there's
derivative.
no taking the derivative here, right? I'm asking, I'm giving you the function f, and I want you to find f of 1, so there's no derivative here at all. And this one, the next one. Okay, so just evaluate it based on what you see there.
Did I do it right?
Yes, and I think.
What'd you get?
Yeah, good job.
Okay. You thought it was gonna take a while, but it didn't.
Don't forget,
Yeah.
when you take the derivative of the integral here,
Ooh. And it's
times 2, right? When you plug in that 2x, you have multiplied by the derivative of the side, so it should be 3 2x squared times 2 minus 5. Because, just like we did up here, for example, let me do it.
Wait, the times 2 comes before the minus 5?
Hold on a second.
thought it was
Please,
everything.
real quick. So,
It should
like we did
happen.
here, derivative of an integral, right? The 3x minus 2 substitutes in for the t.
I don't like you.
Times, though, the derivative of that 3x minus 2. Same idea there, your chain rule kind of thing going on, basically. Yes?
Is this, so I found the derivative, so would I find the antiderivative of that?
Which one are you trying to evaluate right now?
F of 1.
Okay, f of 1, why do you need to find the derivative? You have f.
What?
It's this function, or this
What'd you get?
integral.
3 times.
Taking the derivative will give you f prime. You're doing
For
work
B?
for this problem right here.
You should get a number.
So would I just, where would I plug in 1 for that then?
Well, what's 1 replacing?
I didn't get that.
The X is.
The x.
Oh,
So you have
so
an
it's
x, 1
2
replaces
to
it.
2, which is 0.
You forgot a step.
Oh, 1.
What?
12?
No, you
You get some.
No, you guys are pretty. You
All
forgot
right.
a step. Hunter, you also forgot a step.
Close. This is right.
You get negative 10?
No. Tyler's answer was close. He just forgot one step.
Did?
Yeah.
If you're gonna do it the way you did it
I
here,
just want to keep rank order.
when you, so, okay. Are you trying to use the second fundamental calculus here, or are you trying to do it the long way by actually integrating and then plugging it in? It looks to me like you're trying to integrate it and then plug it in, which you can do, and then take the derivative. The thing is though,
What?
if you integrate this,
No.
it should be,
No.
it should be 3, or it should be x cubed
Because it isn't.
minus 5x.
I wanted to use that
3t
makes sense,
cubed.
but that's like
It'd be
really
t cubed
nice.
minus 5
What was yours first?
When you integrate this,
So-
you plug in minus 5t, and then.
I plugged in 2x.
That's why
Yeah.
you're, you have to adjust it.
So I had 3 times 2x squared.
I know these are wrong.
Okay, so
minus
no, that one's
5.
right,
That
that
one-
one's
and then
right.
Multiply the
This
entire thing
one's
by
not.
2. Yeah, so then you should get.
I'm not sure why I see here.
You
You
should
plugged
get-
in correct, oh, I don't think you want to multiply the whole thing by 2, I think it's just this you want to multiply by 2.
Yeah.
Just that. Because again, when you take the derivative stuff, you separate it by subtraction. So plugging it in, then you multiply the derivative of what's inside, which is
I don't know what
the
I
thing
did,
you plugged
that's
into
what
2x, so it's times 2 right there. So it'd be 6,
7.
2x quantity squared
Not
minus
7.
5, and then
Or
plug in
19.
and see if you see if
No,
that affects
19
you should
is there.
what's the right answer.
No.
Do it.
No. RG's so expensive. That's just one of G.
That's 2 times 2 should be up.
Yes, it should.
Yeah, that's what I was doing, so.
That's why you got, yeah, if that's wrong, it'd be 24 then.
Yeah, that's why.
Oh, I see what you're saying.
Yeah, just do that.
I see what you're saying.
The what?
Yeah, this one.
This right here.
How much? $6,000 expensive.
No, it.
Really expensive, actually.
103,000 miles.
Oh, wait, it is 2 times the quantity. I'm sorry, it is 2 times the quantity.
Yeah, that's what I did.
The whole thing there, it is 2 times the quantity.
14.
So was that right, or
2
was
times
that
the
wrong?
quantity.
Okay.
So, it would be 2
bucket seat,
parentheses
though.
by this whole thing, so it'd be 2 parentheses, 3 2x minus 5, close parentheses.
Why?
Because it's the entire upper limit is 3 times 2x minus 5.
They're expensive
Times
because they're
the side
quality
two.
vehicles.
Then you have the lower limit as well. You multiply by the entire, you multiply the entire limit by that chain rule stuff. So like, hang on. I'll show you.
God, it's so expensive.
It's too much to me just to say. I'll just write it out.
This is clean
That's
stuff.
the one I'm looking at.
No, it's not.
Okay.
Here's the leather interior, but
No, I'm looking at the one.
No.
Okay.
Oh. It's
When
actually
you
a
plug-
metro train.
When you plug this in, I have the 2x, so again, we're taking the derivative of this, with respect to x.
This is really cheap.
Okay. We know these are just going to cancel out, we're just going to plug in our upper limit there. So far, so good, right?
Yeah.
Then you take that thing and times by the derivative of what's inside. Okay? That's what it's supposed to be. That right there, okay? For the same reason, like if I plug, and I can also now I can say, okay, minus my lower limit plugged in, times though what's the derivative of what's inside there is 0, and that's why this whole lower
Here we
limit
go,
just
this is my one.
disappears
Right,
because
you
you're
keep
multiplying that
bringing it.
entire lower limit part by the 0.
Oh.
Okay, that's the idea. Sorry, Christian.
So the answer number or negative 6.
Why is a lot of
Should be 14 is what it should be.
21 for sure.
Probably like 500,000 miles.
No, automatic.
Well, I like-
No advanced.
1 squared, so 1 times 2 is 2, squared is 4, 4 times 3 is 12, 12 minus 5 is 7, times 2 is 14.
It wasn't cheap. 94, 2,500 bucks.
Good.
Oh, this one is damage. Really like cheap. After trying with
Great
Dobby and his
question.
Jeep, I want
So-
so bad.
Let's focus on, what would just, what is f prime of x?
Here you're in that 87. That's good here. That's the obvious here. 87.
What's the derivative of, if that's f of x, what would f
I
prime
just
of
want to
x?
drive around in some.
So not f prime of 1, what is f prime of just x?
$1,000.
Just rolling around.
I forgot how expensive the new ones are.
So,
Really expensive.
well, then you're taking the derivative of an integral though, so you have to use the second fundamental theorem of calculus.
$5,000.
This would be
I'm gonna buy one that's like pretty stock.
So, well, here, let me show you. I did it right here, actually.
Really long one.
Why go to college?
Right, f prime of x is the derivative of that integral, right? If f was this, then f prime is the derivative of that, which, again, okay, following our second fundamental theorem of calculus, the 2x goes into the t, right? Times, so there it is, times the derivative of what's inside the 2,
48.
minus the lower limit with the 2 plugged in, and times the derivative of 2, which is 0, that's why it disappears. So this is f prime of x. All right, if I'm going to find f prime prime, what do I need to do to this?
I've been driving without airbags for I don't know how long now.
Okay, so again, we can do some side work here. So you want to like distribute this through. So
No,
we get
second actually like, well.
like that, right? And then I can like square that out, and so I get 6 times 4x squared minus 10. So it's really 24x squared minus 10.
I don't want it.
So far, so good? That's the first derivative. If I have the first derivative, what do I need to do to find the second derivative?
Decapitating myself on the steering.
Take the derivative of that.
You're gonna do a nice pole over your.
So what is that? It's derivative.
It's that or like my seatbelt.
And now plug in your f prime of 1.
Why is it not?
Okay.
You alright there, bud?
It's gonna be not.
It's just morbidly hilarious.
All right. So f of 1 here is what?
0.
0. Okay? So this is a challenging problem because you have to like each thing requires you to like do something different, and not just different in like a similar way, but different in a very different way. So in this, for example, this first one here, I asked you to find f of 1. That requires you to take this 1 and substitute in wherever you see an x over here. The only place we see an x here is the upper limit. So it'll be 2 times 1, 2. So anytime you're integrating something from 2 to 2, what should that always be?
0.
0. There's no area to accumulate. There's no area there. It's just 2 to 2. Okay? There's no area into the curve there, so it's 0. Letter B, I'm now asking to find the derivative of f and evaluate it at 1. Well, since f is defined as an integral, when I take this derivative, I'm taking the derivative of an integral. When we see take the derivative of an integral, that means we're going to use what? Second fundamental theorem of calculus. Okay? So derivative of this, f prime of x, okay, will be, upper limit gets plugged in, right? Replaces the t. So it'll be 3 times 2x quantity squared minus 5 times that thing, that upper limit, times the derivative of what was inside there, 2. The lower limit will be what? 0, because when we plug the 2 in, it'll be 3 times 2 squared minus 5 times the derivative of 2, which is then 0. So it's just the upper limit there, right? And now I want to find f prime of 1. 3 times 2 times 1 quantity squared minus 5 times 2, which you could stop right there for the free response, or we know it's going to end up being a 14. All right, questions on this one? Are we all okay there?
Bueno.
What we did?
Yeah.
Again, that's where we letter B is where we actually use something we just talked about today, right? This is the second fundamental theorem of calculus applied right here. Now, for letter C, if I want to find the second derivative, well, the second fundamental theorem of calculus doesn't tell us how to find the second derivative. It's only showing us how to do the first derivative there. But we have the first derivative right here. What do we do to the first derivative to get the second derivative? Take the derivative of it. Okay, so I'm going to rewrite this real quick. I think this, what is it simplified to? 2 times 3 is 6. 6 times 2 is, 6 times 4. So we get, what, 24 x squared minus 10, I think. So that's f prime of x. So f double prime of x is going to be what? 48x. And then f prime prime of 1 is going to be then just 48. All right. So letter C was super easy once you got through letter B. All right, questions on any of that? So again, in summary, when you take the derivative of an integral, okay, taking the derivative of an integral, they just cancel each other out. And you plug in your upper limit times the derivative of that upper limit minus the lower limit plugged in times the derivative of that lower limit. So here, because we had x's in the upper and lower limit, it resulted in an upper limit minus lower limit. Here, where we had just an upper limit kind of function, we plugged it in, place of the t squared times the derivative of what's inside 3, but minus nothing, you'll see there, it's just 0. Okay, cancels out because the derivative of 3 will be 0, the lower limit's going to be multiplied by 0. Okay? So, that's it. We still have another 35 minutes, so that means you guys get started on your homework for tonight.
Mr. Webb, we go to lunch.
Oh, 5 minutes. No! You can eat lunch.